In 7.6, we're going to look at other models besides our linear models. So in this section, our focus will be on our exponential and our quadratic functions. We will not be covering logarithmic functions that are in the section of your textbook. So if you see that, you can go ahead and ignore that. So again, we are not covering logarithmic functions, just the two, the exponential and the quadratic function. Now, quadratic functions, I'm assuming that you've seen before, those quadratic equations, but maybe you haven't seen the graph of an exponential function. So let's first review exponents. When we talk about an exponent, and here we have x to the n, that's your exponent, sometimes called a power. And then the x is your base. In this box here, for an exponential function, if the base is b, then it will look like this, y equal to b to the x. But remember, it's a function, so we can always replace y with the function notation f of x equal to b to the x. Here we have to be careful. For it to be a function, the b has to be greater than 0, or it needs to be positive. And then we also have the condition that the base is not equal to 1. So the exponent is going to be just any real number. We'll look at an example here. In example 1, we want to graph this function f of x equal to 3 to the x. Now, I really don't like function notation when I'm graphing, so I will always replace the function notation, f of x or g of x or whatever it is, with y and write y equal to 3 to the x, because I want to get points, and it's easier for me to get points x and y if I'm not using function notation. What I'm going to do is look at some values that we usually use for exponential functions. Usually we'll look at 2 to negative 2. I'll start with the positive values. I'll start with a positive 2, go 1, 0, negative 1, negative 2, and see if these points will give me enough of my graph so I can draw the curve. Now, if I put in 2 for x, remember the y value here is going to be equal to 3 squared. Or in other words, that's going to be equal to 9. So 2 comma 9 would be 1 point. Y equal to 3 to, if the x is 1, that's just 3. So 1 comma 3 would be another point. What about if the exponent is 0? So going back to your algebra, remember the 0 exponent gives you a value of 1. So any number besides 0 to the 0 power is 1. This would be the point 0 comma 1. Now comes the fun part. What do you do with the negative exponent? Then you have to use your properties of exponents. Remember, this is 3 to the negative 1 over 1. To make an exponent positive, you flip everything or take the reciprocal. Well, not quite the reciprocal, because you're going to make the exponent positive. So it's going to be 1 over 3 to the positive 1, which is simply 1/3. Remember, you can be using your calculator as well. But you don't want to write decimal answers. 1/3 is a repeating decimal. You want to write it as a fraction. So negative 1 would be the y value of 1/3. So 3 to the negative 2, negative exponent, make it positive by flipping, is 1 over 3 to the positive 2, which remember, that's not 3 times 2, that's 3 times 3. That's going to be 1 over 9. I'm going to take these points and I'm going to go ahead and graph them. So I have 2, 9, 1, 3, 0, 1, negative 1, positive 1/3. So it's getting really close to the x-axis. Negative 2 is a positive 1/9. that's really, really close. And you can get more points if you want. If I put in a -3, then my y value is going to be 3 to the -3, which would be over 1, and that would be 1 over 3 to the third. So that's 3 times 3 times 3. It's going to be 1 over 27. So very, very tiny, getting super close to the x-axis and a y value of 0. However, it will never equal 0. So if I were to draw this graph, I would just connect these dots. And if you want more points, you can get more points. Maybe you want a +3. If you put in +3, you'll get a +27. But really, this graph is going to keep going. So I'm going to show that by this arrow. And then on the left-hand side, it's going to get closer and closer to the x-axis, but it's never going to cross over the x-axis because the y value will never be 0 and it'll never be negative for this particular exponential equation where it's just the base to the power of x. And that's the graph of the exponential function. Okay, it's going to curve. We're going to look at what happens if we take the base of 3 and we flip it so it's 1/3. Again, I don't like function notation, so I'm going to graph y equal to, ooh, I don't like the green either. I like my blue. I'm going to graph y equal to 1/3 x. I'm going to make a table of values as I did before with my x and y. I'm going to start with 2, go 1, 0, -1, -2. And these are the typical 5 values that I usually use when I'm graphing my exponential function. If you put in 2 for x, then you have a y value of 1/3 to the second power. So that's 1/3 times 1/3. It's 1/9. It's not 1/6. If you put in 1, 1/3 to the 1 power is simply 1/3. If you put in 0, anything to the 0 power is 1. Put in -1, so y is equal to 1/3 to the -1. Remember, to make the exponent positive, we flip everything. So this is the same as 3 over 1 to the +1, which is simply 3. And then y equal to 1/3 to the -2 would equal 3 over 1 to the +2, which is 9 over 1, or 9. If I graph those, I have 2, 1/9, so super close to the x-axis. 1 is 1/3, 0, 1, -1, 3, -2, 9. And now connecting these dots, I have this curve where to the left it's going to continue to get higher, and on the right it's going to get closer and closer to this x-axis, but it's never going to touch it. So think about the values that we had before when we're looking at the base as 3 in example 1. Now when we flipped and we looked at 1/3, what we did is we actually flipped the graph. So this is y equal to 1/3 x. And in our previous, let's see, we had 1, 3, 2, 9. In our previous graph, it looked like this. So that would be the graph in red. That's y equal to 3 to the x. So if you flip the base, you really are just flipping the graph across your y-axis. Okay? And if you look at the ordered pairs or table of values, they're all the same. So that's an exponential function. What it's used for is, I don't know if you've ever heard the term exponential growth. And in fact, something interesting, let's go back to that graph. If you look at the red graph, it's increasing. Originally, when we had our COVID, the number of cases increased exponentially. So the graph was similar to this graph here, except for the base was 2. So exponential graphs show up a lot in nature. If you're talking about the way the mongoose population grows or any population, it typically grows exponentially, meaning it grows really, really fast. Some things decay, and that would be similar to that blue graph. So if you have like a radioactive mass, the amount of radioactive material will go away over time. So that's what we call radioactive decay. So these functions show up a lot in nature. Now the next one we're going to talk about is the quadratic function. So the quadratic function is something I'm assuming that you guys have seen. Quadratic functions look like this: y equal to ax squared plus bx plus c. Or you can replace the y with the function notation f of x. A, B, and C are real numbers. Here, A cannot be equal to 0, or it's no longer quadratic, it would be linear. And the graph is a parabola. Let's go ahead and review what that means. If your A value, so that would be the number or the coefficient on the x squared, if the A value is greater than 0 or positive, what that means is your parabola will open up. It will look like a smile, right? Because this is positive and positive people smile. So you're going to get this opening up graph. So I'm just going to draw a random parabola. Maybe I'll start here at 2, -1, draw some points, and go up from there. So this is just, you could draw it anywhere on that graph. So this is an example of a graph of a quadratic function that opens up. The lowest point, if it opens up, is called our vertex. And then in this particular parabola, I have 2 x-intercepts and I have 1 y-intercept. When you graph a quadratic equation or quadratic function, you'll always have 1 y-intercept. Sometimes you'll have 2 x-intercepts, sometimes not. So I could also draw a parabola opening upwards but above the x-axis. Notice that in this case I still have a vertex, and since it keeps growing and growing and growing, eventually it will cross over the y-axis, but I don't have any x-intercepts. It's also possible that you could have just 1 x-intercept, and that would be if the vertex is actually on our axis. So you could have 1 x-intercept, 2 x-intercepts, or no x-intercept in a parabola, but you always have 1 y-intercept. Now there's an important line that passes through your vertex, and I'm going to draw this dotted because it's actually not part of the graph of the parabola. Of course, I hand drew my parabola, so it doesn't look that nice. But imagine folding along that vertical line passing through the vertex. The 2 sides of your parabola should match up. What that means is all points come in pairs. So looking at our graph, we see our x-intercepts. I have one unit away to the left, and the other one is 1 unit away to the right, meaning you have pairs that are the same distance away from your axis of symmetry. So this is what we call the axis of symmetry. The only point in a parabola that does not have a pair, notice that all these points come in pairs that are the same distance away from our axis of symmetry, is our vertex. The vertex is the only point in a parabola that does not have a pair. Let's look at what happens if our A value is negative. So in that case, it's going to open down. There's negative people frown, so it should look like a frowny face. And I'll just draw a random parabola where notice we still have a vertex, but in the case where it opens down, the vertex is actually the highest point. And there's still the same axis of symmetry, which passes through your parabola, and all points on either side of the axis of symmetry, they come in pairs. Same thing, it's possible for us to have two x-intercepts. It's possible for us to have no x-intercept. It's possible for us to have one x-intercept, but always just one y-intercept. Graphing a quadratic function is kind of a lot of work compared to the exponential functions. Exponential functions are easy. You just put in x values, you get back your y values, and you plot the points, draw your curve. It's either going to go up or it's going to go down. With a quadratic function, you want to first note if it's opening up or down. Okay? And that would depend on that a value, right? So that would be, is your a value, is your a value greater than 0, or is the a value less than 0? That's what we're looking at. You want to find and plot your vertex because that's where you start. Okay, you start at your vertex. If it opens up, you go up from there. If it opens down, you go down from your vertex. To find the vertex, you're going to use x equal to b over 2a, and it's going to be a negative, so negative b over 2a. Once you find that x value, you would put into the equation to find the corresponding y value, because remember the vertex is a point. It's a point xy. So you don't only find the x, which is sometimes the error people make. They find the x and that's it. Remember, you need an x and a y, they have to go together. So some nice points would be the y-intercept. Remember, that's really easy. You just put in 0 for x and you'll get your c value in the quadratic equation. And that's true for any equation. It doesn't have to be linear, be exponential, it could be quadratic, it could be any equation at all. To find the y-intercept, you always put in 0 for x. To find the x-intercept, you always put in 0 for y. Now, how do you find the x-intercepts? So this is where we're finding some points, basically to determine how wide our parabola is. We have the vertex, we know where we start, we know whether it opens up and down, so we know if we're going to draw the parabola up from the vertex or down from the vertex. We just have to know how wide it is by finding other points. So the x-intercepts are found by, remember, we let y be 0, and we solve the equation for x. Now, if you know how to factor, you can try factoring, but that doesn't always work. Not all quadratic equations are factorable. What does always work is this quadratic formula. So going back to the quadratic formula, remember the x value, and we're finding our x-intercept, is equal to negative b plus or minus the square root of b squared minus 4ac over 2a. So where does this formula come from? This should be a familiar formula from algebra, but remember what I said is all points come in pairs, and that's where this plus minus comes in. That gives you 2 points. So it's possible that you can have two x-intercepts. Now, in the event b is 0, that first part goes away and you just have one x-intercept. Or it could happen that you have no x-intercept because what's underneath the square root might turn out to be negative. So remember, you can't have a negative underneath the square root. So putting that aside, notice that x equal to negative b over 2a, that was the vertex. Notice that if I took away the plus minus square root of b squared over 4ac, if I just took all this away, then I have negative b over 2a. I have the x value for the vertex because the vertex is the only point that is by itself. It doesn't come in a pair, so all you have to do is simply take away the plus minus portion part on your quadratic formula. Now, going through all these steps, you may not get enough points to graph. Sorry, let me go ahead and get rid of this as well. It doesn't have to do with the x-intercepts. So if you were to connect the points and you still don't have enough information to complete your graph, then you might need some additional points. So it's easiest to go through these steps by looking at an example, and we'll just do a couple of these. We want to graph this quadratic function, which is y equal to x squared plus 6x plus 5. Well, first of all, I am going to write down, just because I'm going to refer to it a lot, my a value, which is the coefficient or the number on the x squared, so that would be a positive 1. My b value is a positive 6, and my c value is a positive 5. So open up or down? Well, a is a positive 1, so this opens up. And that's the first thing I always do, because then I want that picture in my head of something opening up. If when I compute my points, I don't get that, then I know I did my math wrong. Where's our vertex? So remember, the vertex is an x and a y value, where the x value is negative b over 2a, which is why I specifically write down my a, my b, and my c value. So this would be negative 6 over 2 times 1. So negative 6 over 2 would be a negative 3. So I have the x value of negative 3. How do I find my y value? Well, I have an equation. Y equal to x squared plus 6x plus 5. So to find my y value, I'm putting in negative 3 for x. So remember, the negative 3 goes in for all of the x. So that would be in parentheses squared, plus 6 times negative 3 plus 5. So that's going to be a positive 9 minus 18 plus 5, which should give me a negative 4. So negative 3, negative 4, that's going to be my vertex. And I know I'm going to go up from there. So all I need is additional points to determine how wide my parabola is. Finding the y-intercept is always very easy, because remember, to find the y-intercept, you're putting 0 in for x. So if you go back to the equation and you put in 0 for x, you'll have y is equal to 5. Y is always equal to this c value, which in our case is 5. And here's my y-intercept. Now you should get probably around 5 points to get a nice graph. Let's think about what we have so far. I'm not even going to find the x-intercepts yet. Remember, my vertex has this imaginary axis of symmetry, this vertical line that passes through the vertex. And the property is that if you have one point to the right, notice that we have this point 0, 5. If you have one point to the right of the axis of symmetry, you're going to have another point to the left the same distance away. So if this is 1, 2, 3 away, then I go 1, 2, 3 in the opposite direction, and I have my other point. Now this is going to irritate me showing that red line. So I can see what my graph will look like, and I can draw it right now, but oftentimes you'll be asked to also identify your x-intercepts. So how do we find our x-intercepts? Well, you could try factoring. Take x squared plus 6x plus 5 equal to 0 and factor if you know how to factor. But if you don't, then to find your x-intercepts, you would need to use the quadratic equation, where you're putting in the a, the b, and the c value that you have listed. So if you're using the quadratic equation, and maybe I'll go ahead and do it off to the side here because I think I'm going to need a lot of space. It's going to be x equal to negative b, so negative 6 plus or minus the square root of b squared, so that would be, oops, positive 6 squared minus 4 times a was 1 and c is 5 all over 2 times a. So my x value would be negative 6 plus or minus the square root of 36 minus 20, all of this over 2. So oftentimes people will just write the fraction bar underneath the square root portion, but all of it's over 2. This simplifies to negative 6 plus or minus the square root of 16, whole thing over 2, which would be negative 6 plus or minus 4. So let's see what that means. That plus or minus says I can break this up into 2 pieces, where the x is equal to negative 6 plus 4 over 2, x is equal to negative 6 minus 4 over 2. X would be equal to negative 2 over 2, so this is going to be 1, or negative 1, sorry. And the other one would be x equal to negative 10 over 2, so negative 5. The point would be negative 1, 0 if we write it as an ordered pair, and negative 5, 0, but oftentimes in my lab they just want the x value. So if they're asking for the x-intercept, oftentimes I'll just have you list negative 1 comma negative 5. Okay, so let's go back to our graph and see if these points make sense, because usually finding the x-intercept is the hardest part. So negative 1, that makes sense with my graph, and the negative 5 makes sense with my graph because these points go upward. Give me a graph opening upward. Okay, so open up or down, find your vertex, then find your y-intercept. Save the x-intercepts for last because they're the hardest ones to find. Okay, loud rooster today. So example 4 is in function notation. Remember, I don't like function notation when I graph, so I prefer, you might not, but it's easier for me to just replace the f of x with y. And again, I'm going to write down that my a value is negative 1, my b value is 2, and my c value is 3. I want to write that down for my reference because I can clearly see that a is negative, so this opens down, which means I'm going to get a frown. So if my points don't line up to something opening down, I got to double check my math. Let's find our vertex. So remember, that's going to be an x and a y value, where the x value is negative b over 2a. So negative b is 2 over 2 times a is negative 1, which gives me negative 2 over negative 2. It's going to be a positive 1. So it's 1 comma, find your y value by putting in 1 for x in the equation to get y equal to negative. And here the 1 has nothing to do with the negative in front of that x squared. If the negative x was in parentheses, it would, but the negative is not. So it stays outside of your x value. Squared plus 2 times 1 plus 3. It's still going to be negative 1 plus 2 plus 3. So 5 minus 1, that should be a positive 4. So just be careful when you're plugging values in to the x squared term. The vertex is 1 comma 4. And I know this is going to go down from that vertex. So let's find some points to see how wide it is. Again, the y-intercept is always the easiest because you're just putting in 0 for x, which just gives you that c value of 3. So I know that 0, 3 is my y-intercept. Again, I have that axis of symmetry going through the vertex. And since I have that y-intercept point 1 unit away to the left of my axis of symmetry, I'm going to have another point same distance away to the right of my axis of symmetry. Those points are kind of close together, so again, I'm going to find the x-intercepts to get a better idea of how wide this is. So x is equal to negative b, which is negative 2 plus or minus the square root of b squared. So 2 squared minus 4 times a was negative 1 and c was positive 3. All of this over 2 times negative 1. That would be negative 2 plus or minus the square root of 4 plus negative times negative is positive. 4 times 3 is 12 over negative 2. Negative 2 plus or minus the square root of 16 again over negative 2. Negative 2 plus or minus 4 over negative 2. So again, this gives me two values. The first value, x equal to negative 2 plus 4 over negative 2. And the other x value is equal to negative 2 minus 4 over negative 2. So I have x is equal to negative 1 and x is equal to a positive 3. So the negative 6 over negative 2 is positive 3, which gives you the point negative 1, 0, 3, 0. Let's see if those values make sense with my graph. So negative 1, 0, positive 3, 0. Yes, it does. I have on my graph points that show parabola opening downward. Huh, crazy roosters again. And that's pretty much it for this section. This section was just focusing on exponential and quadratic functions and their graphs. So that's it for chapter 7.